Okay, so last class we were start discussing on digital and analog 01, 01, why we need to consider everything in 0 and 01 ways. There were a few examples starting from sound wave, right? How do you convert an analog signal into a digital sound? Textbook also mentioning on MP3 files or WAV files that you can easily download and listen. This was one of the examples that I gave you last time, right? So amplitude, period, and frequencies, those three characteristics of the sound signals. And then what was the main point of doing this? How do you reproduce the original sound into a digital format? What was the technique to do this? Sampling was the word to describe it, right? Sampling. You get a certain point and you get the value. You store that value, and then later, if you want to reproduce the sound, then you can just reconstruct the signal looking. Of course, it will not be exactly the same looking as the original one, that curvy graph, but we can make it close enough in terms of MP3 files that your human ears will not make a difference, will not hear a difference between the original and digital sound, right? What was another technique? The quality of this was depending on two factors. What was the two factors? Quality of reconstructing this sound wave. 뭐였지? 바로 전장에 있을 텐데, probably on the previous page. Sampling ratio and that's the when you try to record the value of, in this case, value of y-axis, how many digits are you going to store, right? In theory, if you do a sampling ratio really tight, then you might be able to get the original sound. Right? I also mentioned something like MP3 files and some of the new file formats like FLAC, FLAC, 맞나? I don't know how to pronounce that, but it's something like you don't lose any 무손실, lossless means maybe they are close enough to do similar reconstruction as the original sound, right? You go, how do you draw this? How do you represent this? I mean, if I ask you to give me a function to draw this type of lines, what do you need? Like if I ask you a question, give me a function to describe this sound. 뭐로 해요? What do you need? Sine, cosine이겠죠, isn't it? Right? How do you change the frequencies, amplitude of those stuff? You change the parameters of those sine, cosine functions that you will have what you want. Binary number system, and then we start discussing like this images. I also told you pixels. Well, it's like a numbers, right? Two-dimensional numbers. We also try to draw a grid. Each column, each box that we can write a number, something like this, and then it will construct a big picture that you see on your screens, right? We know all this, so when you're storing an image, you're basically storing a set of numbers in two-dimensional formats. You can construct a three-dimensional images, right? 3D videos or 3D movies, which is typically much larger in terms of file size. So that's because we need to store more numbers in it. And also your CPU try to convert that number information into like colors. That's why when you see a movie files, they constantly takes a CPU time. Anybody try to, let's say, try to open up any movie player, Go player, and while watching, you play on some movies, and then you try to take a look at the CPU usage while you're watching those movies. Constantly 20 to 30% is doing something, means computing those numbers, images. Because like I mentioned, movie file is actually it's a group of images, right? Group of frames. Keep moving. 그죠? 곰플레이어 같은 거 보면 CPU 막 20-30% 계속 하고 있죠. So did I also mention if you buy a bit more expensive graphic card, what do? Bit more expensive graphic card. They say its graphic card has its own CPU, something called 뭐라 그러지? GPU, see? Now you kind of understand why those type of specialized GPU processes doing what. If your graphic card has an extra CPU, those CPUs are doing a lot of mathematical computation, adding multiplication of those image files. 그죠? If so, then your CPU can do other stuff. 그죠? GPU는 아마 수학 같은 거 할 수 있게 특별히 설계된 CPU 이렇게 보면 되겠죠? 그죠? And then blah blah blah, loss this. And then the reason we were discussing was eventually we want to build something, a circuit using this type of gates. What was the basic gate that we covered last class? 뭐였지? What was the gate that we tried to cover? 뭐 이런 거였죠? AND gate, NOT gate, OR gate. Combination of these gates that we might be able to get what we want. Again, we're not going to go into in too much in detail for truth tables, but thing is, if you want to build certain circuits, you need this type of representation before you actually using those gates to implement. Like whatever this does, only thing that I'm interested in is which combination of inputs will give me output 1 to be 1. So I only take these two rows and try to build the circuit from backward purposes. Again, this will be covered in other courses, probably the second term or next year courses. Here are the examples that we might be able to use. This is addition circuit. In order to add something, it's the only thing you're adding is 0 and 1. So if your input values A, B, and C, okay, if your input values are 0, you try to add A and B. Of course, your output will be 0, 0, right? This will be your truth table. A0, C. C is 1, carry bit. The 1 is carried from previous computation. Then I should put that as a sum digit. 그죠? 11 더해서 10 넘어왔으니까 앞에 1. Right? Carry bit will be 0. Same thing. 1, 1, 1, 0. 1, 1 will be 0, 1 carry bit. I am going to have to tell the other carry bit, next carry bit to be 1. 더하기 하는 거예요, 더하기. 1 더하기 0은 1. 그죠? 1 더하기 0, 1 더하기 1은 1이니까, 0이니까, 1 더하기 1은 1, 0이니까 0 쓰고 다음 넘어가는 게 carry bit 1. 그 얘기 하는 거예요, 그 얘기. So this is the add circuit. Circuit that doing a addition need this type of output format. So this truth table, we can build whatever gate needed from inside. 여기에 AND gate 어떻게 넣고 OR gate 넣어서 output 나오게. So probably I'll be considering this 1, 1, 1, 1 first. And then 1, 1, 1, 1. Which case will I have a carry bit to be 1 again? this point, okay, it's okay. That's just example. I don't think they even textbook provides you those details. Maybe AND gate. Maybe AND gate. Add gate. gate란다. Add circuit. I'm sorry. Add circuit. Should be on. Okay. So we're gonna start discussing on some different type of circuits. Something called control circuits. The previous circuits that we have looked at is doing something. Addition, we could make an add circuit. You could make other type of circuits using AND gate, OR gates, NOT gates, or XOR, NAND, whatever you got to use. So there are different type of circuits that you can do, which doing a decision making. So control circuit makes a decision, determine order of a operation, select data values. Graph will be much easier to explain, but let's see. Multiplexer, something called multiplexer, is a control circuit. Selects one from among many inputs. From two N input lines, there are N selector lines, and then you will have only one output ready. So later, when you see a multiplexer circuit, they're gonna draw a big box like that, and there are many inputs coming in, which is 2 to the N. There are N inputs, and you're gonna select one of them to be a output. That's a different type of circuits. Why do you need a control circuits? Later, you will be dealing with many different circuits, and you wanted to just choose one of them. This control circuits will do that job. Each input lines corresponding to unique pattern in the selection lines, input values passed to be output. We'll see. So say select one value from among a many different input values. Easily put as this. This is input value 1 and 0, A and B. I'm gonna choose one of them. I'm gonna send some signal, choose one of them to be an output. Okay. 그냥 여러 가지 들어오는 것 중에 하나 고르는 서킷 이렇게 보면 돼요. 그 two input multiplexer circuit. 그래서 이거를 어떻게 구성했는지는 이거는 괜찮아요. 우리 이번 학기는 몰라도 돼요. It's not our concern. But important thing is this one I will collect. This one. With this input, I can control this input, which one to be output later. This is multiplexer circuit, control circuit. Okay, I have 4 different input. This is called register. This is place that I can store. I like to send some signal that choose one of them. What if I wanted to choose the third one? What signal can I send? 간단한데. If I wanted to send that third one, maybe it's in the select line, I'm gonna send one zero. Why? For example, why? If I wanted to see this R2, I'm gonna send 1 0. Why? 0 0 0 1 1 0 1 1. 4 of them. That's it. 그거 다 하는 거야. That's multiplexer. That's what we're doing. So among this input, I like to choose the third one. If I wanted to see the first one coming out from the circuit, 0 0. Okay. Something like that. That's a basic idea of circuit designing. Okay. Example of use of multiplexer circuits. 이게 웬 뒤로 가 있네. Or the other way around. Decoder sends the signal out to the only one output, choose by its inputs, and input lines to the output lines. So you can flip the circuit in a different way. Each output line corresponding to unique pattern of the input lines. Only the chosen line of produce 1, all others output 0. Graph similar. Graph looks better. 거꾸로. 내가 여기서 뭐 줄지를 보고 코드가 이렇게 나오고. 주는 게 여기는 n이 2n이고 나올 때는 n만 나오고. 반대는 방금 반대였죠. 2n이 들어가고 하나 n 개만 나오고 멀티플렉서의 반대라고 보면 돼요. 멀티플렉서의 반대. Operation goes 0, 0, 0, 1, 1, 0, 1, 1. That would do 1, 2, 0, 1, 2, 3, just one values only. 여기서 뭐냐? 디코더 서킷 하면. So if I send a signal 0, 0, decoder will give me to the add circuit. If I give the value of 1, 0, 1, then subtract circuit. 1, 0, multiple circuit. That's a decoder circuit. It will come up in the next chapter that we'll be covering today, machine languages. It'll be much clearer on that part. 사실 그게 먼저 나왔으면 훨씬 쉬웠을 텐데. 여기도 it's okay. So just look at the shape of these two different control circuits, decoder and a multiplexer circuit. 그리 중요하지 않아. 내가 뺄까 말까 하다가 그냥 넣어놓은 거니까 그냥 참고 삼아서 봐요. Okay, what's important is whether we understand the binary formats. Why do we convert everything into a binary number, 0101, digitalized data formats? You're basically working with all these 0101 numbers. Computers use a binary representation because they maximize reliability of the electronic systems. Well, it's the only way to represent the data in the electric systems, right? Electricity on and off, 그죠? Either 0 or 1. That's the only choice. Many kinds of data may be represented at least in approximate digital format using binary values. So if you download a poor quality of MP3 files, usually file sizes are smaller. Maybe they do a less sampling of those audio that they can collect. Boolean logic is being used to design a circuit, truth table. In which situation I like to have a 1, which situation I like to have a 0, depends on what you want to build. We briefly look at add circuit. If you want to build an add circuit, then you also need to consider how many input values in your add circuit requires. So, and then you start doing it. 아까 전 같은 경우에 add circuit은 예를 들어 5 digit add를 하고 싶으면 어떻게 해요? 예를 들어 I like to build a circuit of doing this addition. 그럼 어떻게 하면 돼요? What would you do? How do you use that add circuit we briefly looked at to do this? Well, maybe I need 5 add circuit. Add circuit. 아니다. 3개지? 그림을 잘 못 그려서. Add circuit. 그죠? A, B, 미쳤구나. A, B, C. 그죠? A may be here, B may be here. 그죠? S value will be here. It will have a two outputs, right? S will be here. This was what? 여기 뭐였어요? What was this place for the output circuit or add circuit? 뭐였어? 뭐였어? C지 뭐야? C 아니었어요? Carry bit C for the add circuit. Or no? 맞네. A, B, C. Carry bit A, B, C. Okay. S 여기지? Sum of the digits. S will be here. So, carry bit should be going where? Carry bit is going to where? 어디 가겠어요? I need to do this second step. So another add circuit. this. 0, 0, right here, and then go out. Another S2, carry bit going to another add circuit. Carry bit goes to another add circuit. Add. 그지? S3, S4, S5. Carry bit in front. 아니야? You just build a circuit of doing 5-digit additions. 그죠? add circuit 5개 이렇게 붙이면 이거 구현할 수 있죠. 그죠? You just build your calculator. Just build your calculator. Very dumb calculator with the 5-digit addition possibilities. 그냥 전선 이렇게 연결하면 되는 거야. 여기 값 나오는 거 여기로 가야 되잖아. 여기서 C로 가야 되잖아. 그 다음 디짓, 그 다음 디짓, 그 다음 디짓. 여기서 나오는 값은 S 값은 요 아래로 떨어질 거고 값하고 나중에 여기서 나오는 캐리 빗 여기로 들어오면 딱 되잖아. 그죠? 이렇게 하면 이렇게 원빗 애드 할 수 있는 서킷 가지고 서킷 그러니까 회로를 가지고 하나 할 수 있는 회로를 5개 붙여가지고 5비트짜리 애드 할 수 있는 더하기 할 수 있는 서킷 만들었죠. 그죠? 물론 여러분들이 만들면 중간에 여기서 어디 연기가 올라올 거예요. 타가지고 보드가 실제로 구현하면 뭐 암페어도 신경 써야 되고 뭐 이상한 거 있잖아요. 물리에 나오는 거. 물론 타겠죠. 중간에 어디서. 중간에 0이 1로 바뀌고 막 이런 경우도 많을 거예요. 그 보면 트랜지스터 구현하는데 이렇게 보면 뭐 레지스턴트 막 이래갖고 이렇게 잡아주고 막 이런 거 잘못 꼽으면 0이 1이 되고 1이 0이 되고 없어지기도 하고 막 그래요. Okay. In this chapter, they just wanted to show you some of the basics of doing this. We can build a logic circuit that acts like a Boolean operator using transistors, right? Small device transistors. AND gate require 2 transistors to build an AND gate or something. There, OR gate 2 transistor, AND gate 3 transistors. It's written somewhere in your textbook too. Circuits may be built from a logic gate. Circuits can be building using this type of gate. And it basically gives you 1 or 0. It will be your design to build one. And then we briefly looked at control circuit, but we're not going to ask too much about these control circuits. So basically selecting certain inputs from your design. Okay, that's it. That's it. So chapter 5, let's go to chapter 5. So in this chapter, you will learn about components of the computer systems, which I mentioned already briefly throughout the first 2 weeks. So you guys know it already, and some of you know this already from other stuff in your high schools. So it's nothing new. What is a von Neumann architecture? This is famous architecture. Which is your current computer designing? What does your current computers have? CPU, memory, keyboard, I/O device, screens, right? When you turn on your computer, do you need to insert any disk? No, right? Those programs already within the memories and stuff, right? Those type of architecture who propose this type of von Neumann architecture. Non-von Neumann architecture. Things require heavy computation that your normal computer design may not be suitable, not that best suitable for those type of problems. We take a look at it. I think in your second year there is a course called Computer Architecture. 맞나? Computer Architecture 맞죠? 2학년, 9학년들 우리 2학년 때 컴퓨터 아키텍처 있잖아요. 그죠? Computer architecture, there is an area that study for the computer architecture, how the things should be designed. So they concern with the, sometimes they start from this digital circuit designing, truth table, and then it goes to how the memory should be built and how the memory and CPU should be interacted between each other. Those types of stuff is also another area to study the major functional units and how they work. That's the area for computer organization or computer architecture. It requires an important concept for abstraction. Well, it's not the only, not just computer organization area requires this concept of abstraction. When you're building an algorithm, when you're building a pseudocode, abstraction, you already are doing abstracting the problems. What is abstraction? Probably textbook provides a definition, it's not clear to you. What is abstraction? abstraction가 뭘까? When you try to build some solution to a problem. Simply put, you want to simplify the problem, so hopefully you can find an easier solution to apply. So actual real world problems are very, very complex, right? Very, very complex. But I like to tone it down to very simple designing. Only requires maybe node and the edges between the node. So used throughout the computer science, without it, it would be virtually impossible to study computer design or any other large complex design. When you see your movies or famous stories, 그런 거 보면 막 나 최근 영화를 본 적이 없어. 그런 거 보면 막 그 카페 같은 데서 막 아키텍트라는 사람들이 소프트웨어 만드는 사람이 막 이런 거에 막 그려가면서 막 이렇게 얘기하잖아요. 이게 이렇게 하고 이러고 다 했다 이래요. 그렇죠? 다 했다 이래요. It is also a type of abstraction. They may be referring to certain modules in their software is calling the other parts. But without this type of thinking, it's quite difficult to communicate to your coworkers. Actually, when you take a look at some big software designing documentation, they all look like this. They do not care about any detailed structures like what type of C code, what programming language they're going to do this. 실제로 이 안에 들어가는 뭐 예를 들어 소프트웨어를 만드는 사람도 이렇게 많이들 그린단 말이야. 근데 그 사람들은 이 안에 뭘 어떻게 짜고 이런 건 신경 쓰지 않아요. 신경 쓰지 않고 그냥 이렇게만 크게만 그려. 얘는 얘를 부르고 얘는 얘를 부르면 이렇게 짜면 되겠네요. 땡이야. That's architecture. 실제로 이 안에 짜려면 엄청 힘들 거 아니야. 뭐 C로 짤지 뭐 할지 C로 짜도 엄청 힘들고 그런 거는 잠깐 잊어버리는 거예요. 잠깐 잊어버리는 거예요. 할 수 있다는 거. So that's probably one of the most things that I heard when I was in first year students in university. Professors always come to class and they always emphasizing on the fact after graduation you guys should get the job as a software architect, not the developers. People who's doing that, not actual coding. 맨날 1학년 때 내내 들었던 말, 졸업할 때까지 들었던 말이 그 말이었던 것 같아요. 실제로 코딩하는 사람이 되지 말고 코딩을 어떻게 하는지 가르쳐주는 이런 거 그리는 사람이 되라고 그랬는데 이게 쉽나? 잘 안 돼요. 경험도 많이 필요하고. Abstraction. Abstraction. Systematic view within this system or CPU or whatever software. I don't care the abstract view like this. Abstract view like this. Quite simple designing. So they can, the basic idea of doing this is in order to communicate with the others, communicate with the people that you're working with. 아주 간단하죠? Just simple and node and edges will present the problem. I forget about any difficult stuff when you're actually doing this type of stuff. So that's a brief idea for abstraction. We will hear this term again and again. So component of the computer systems, von Neumann architecture is based on following three characteristics. Things that we already know. This is the guy who proposed this idea. We've probably seen this guy somewhere in the YouTube clips that I show you when we're doing the ENIAC. What was the video of that we saw? ENIAC, right? Somewhere in the video, similar video, they mentioned of him too, von Neumann, the guy who proposed this type of architecture. And they said he had the photographic memory of everything. photographic memory가 뭐지? 그냥 보면, 글을 보면 그냥 그림으로 다 외우는 사람이래요. 그냥 몸은 다 보면 다 외웠던 사람이래요. He also built a very big computers when the early 1950s, 40s. So this guy who, the genius, he said we need this type of architecture for future computers, which is like 4 major subsystems called memory. You need a memory, input and output, and arithmetic logic controller units, ALU, which is CPU, like today, and other control units, and store programming concept. Store program concept. All the programs will be stored within the memory, so they will do it. So when you turn on your computer, you would like to open up a Microsoft Office, for example. Double-click Office, right? It opens up. It's already somewhere in your memory. You just called. You're seeing it on your screen. It means it's on the memory. He actually proposed a concept. So proposed the entire architecture of today's computers as it is. And also, the programs are able to do a sequential execution of the instructions, which is also quite similar to the programming assignment that you do, right? Line 1, 2, 3, 4, 5. Sequential execution of the instructions. See? 위에서부터 아래로, top down. They do something, right? So it's pretty much he proposed everything. So computers today, it follows a von Neumann architecture that we know. And typical graph. Memories, control unit plus ALU is CPU. ALU, arithmetic logic, 맞나? Arithmetic logic units. 갑자기. Arithmetic logic units. So what do? Arithmetic, addition, subtraction, those type of simple operations. Control units, maybe they using a decoder multiplexer and somehow sending out the signals to different components, each component maybe. Components of the von Neumann architecture. It's used everywhere, right? It's not so much different from today's design. What's this on the top? The line that connects all three components. 저거 뭐야? What is on the top? Anybody building your own computers? 컴퓨터 보드 이런 거 안 사요? Did you guys buy board? 조립 컴퓨터 하는 사람 혹시 하죠? When you try to buy those board, what are you usually looking at? What is the first thing that you looked at in those board? 뭘 보고 사요? Price? Cheapest? Graphic card? 하긴 요즘엔 다 내장 다 돼 있죠. 그래픽 카드 이렇게 박아갖고. 근데 그거 별로 좋지 않잖아요. 그죠? 그래픽 카드, Lines, yeah, lines. It's something called bus. So when you take a look at carefully on those specifications on the computer board that you buy, some boards are expensive than the other board. Why? They have a large bus speed. So data exchange between these components faster, larger. If you buy those stuff, it's a bit expensive than the others. The PCs, your personal computer board are cheap. 얼마냐? Less than $100. 한 10만 원이나 하나? Right? Less than $100. But if you maybe are building a bit bigger computer, the board may be $1,000. Just because they have a large bus and there's more place to put this type of stuff. 뭐야? 좀 비싼 보드면 PCI X 이런 게 꼽을 때가 좀 많죠? 많이 꼽으면 어떻게 돼? 그래픽카드 막 두세 개씩 꼽으면 어떻게 돼요? 버벅거릴 수도 있겠죠. 길이 좁아서. 버스가 일반적으로 크면 보드가 좀 비싸요. 이제 애누리 이런 데 가서 버스 스피드 나와 있는 거 한번 봐봐. 비싼 건 좀 많이 나오고 뭐 메가헤르츠, 기가헤르츠 이렇게 써놓고 하는데 그 차이예요. So memories and cache, memories and cache. Things that we already know. 주족이다. Memories. Function a unit of computer that stores and retrieves the instructions and data being executed. What is a memory? What is a memory? 메모리가 뭐야? Storing units. What are they storing? Huh? 0101, right? 0101. RAMs, memories, right? They store a 0101 somewhere in their chips. That's a RAM that you just saw. Access technique used by computer systems. Read-only memory, ROM. Another type of memory information is pre-recorded during the manufacture. 쉽게 말하면, what do you say that? You burn the chips. You're burning the CD-ROM, right? That's the common term we use. Also, burning the chips. Too. Memory is actually 8 bits cell size. 그런 얘기 많이 하잖아요. 뭐 새로 나온 메모리 4기가, 뭐 세계 최초 16기가, 뭐 32기가, 뭐 이런 메모리 얘기 많이 나오잖아요. What does that mean? What does that mean? Within a given small space, you build a technology to store more bits in it. That's what it means. So the largest unsigned integer values that can be stored in a single set for 8-bit is 255. 2 to the 8, 2 to the 8th. 0 to 255. So we're going to use that as an address of the space. So later when they draw a memory in board like this, they do it like this. 0225. Like this. 뭐 이런 식으로. It's a memory space that I draw. Of course I can store 0101. Somewhere in here, maybe 64. I follow a memory space, and your program is stored here. Usually, your operating system stored on the top like this. Let's say this is what is the typical memory size of your computer? 한 2기가? Let's say 2 gig. OS here, operating system here, your Microsoft Office here. This is how your memory look like. Okay. So range of addresses available on a computer when dealing with the memory, distinguish between addresses, contents of that memory address. Like that. So it requires something called register. It's a storage location for this MAR, memory address register. So there are small space. So in this space, I can write down the memory location, memory address. So next time I look at this place, okay, I go to 2. Next time this was saying 4, then I can go to 4. There are 2 different type of registers in this case. The first one is memory address register. The other one is MDR, memory data register. They actually store a data. But registers are usually very small size memory, very small size memories. There is also different type of memories, right? Cache memory. When you try to buy CPU, what is the thing that you're usually looking for? CPU 살 때 뭘 많이 봐요? Clock zoom, right? How fast it can go. Also, sometimes it's the same type of speed. Some CPUs are a bit more expensive than the others. Usually then the difference between the two is cache memory size. So this is typical memory representation for RAM that you can use in your computers. Okay, so again, we're storing just 1 bit at a time. 8-bit, 1 bit, 1 bit, 1 bit, 1 bit. So, depends on the n, it will give you the maximum memory size. And to the 16, 20, it's obvious, right? 이만큼 you can have this large numbers of range for the memory addresses. Memory and cache continues. Basic memory operations. What are we using memories for? What are we doing? Again, what are we using memories for? Store, right? We put the program in. Put the program in. And they add another one, fetching. What is a fetching? When you close a Microsoft Office, what happens in your memories? Maybe it disappears for a while. Free space. Some other program maybe can get in, get the memory space. Right? Memory usage can be easily checked on your computer too. Again, 오늘 많이 가네. Let's go back to Windows. This is telling you how much memory each program it takes. 그죠? Internet Explorer is getting 62 megabytes. They take 62 megabytes within this memory space. SBC host is a Windows process. 뭐 알만한 거 있나? 뭐 있을까? 어떤 거? Explorer, yeah, Explorer. 탐색기. 탐색기는 무슨 욕 같다. 탐색기는 takes 17 megabytes, right? So any process running at the same time in this computer needs to be in the memory. That actually tells you how much it takes from a memory. If I kill one of these programs, what happens? Take it out. I'm removing it from a memory. It's no longer being run this time. 그죠? If you look at this list of process names carefully, maybe you might be able to find some viruses running behind. 많죠? 이거 하는데도 이렇게 프로그램이 많이 돌고 있네. So that's a basic memory operation, fetching and storing a data. Right? Programs also have a data too. Memory access time, typically 5 to 10 nanoseconds. It's quite fast, really fast. Access means I go read. Memory registers, usually used to implement the fetch and store operations. There are special type of memory location called register that I write something in it. Like those things that we saw, memory address register, memory data register, usually very fast memory spaces that we can use. 여기 나오네. Memory address register hold the address of the cell to be fetched or stored. It have a location of the memory. It store a location of the memory space. MDR contains the data values to be fetched or stored. Two-dimensional structures. Why it says two-dimensional structures? Why do they say memory two-dimensional structures? two-dimensional이지 뭐. X and Y. 그죠? Two-dimensional structure. That's the one. And they say store in row major ordering. Row major, column major. Row is what? Row가 뭐지? Row, column, right? So they store a data in this row major ordering. That's what it means. 줄을 기준으로 한다. Selection lines, row selection lines, column selection lines. So maybe I put out the row first, and I maybe there is another line says the third row, fifth one. What's written on there? So So row selection line, column selection lines. This, something like this is possible. That's why we briefly looked at for decoder and multiplexer examples later. 요 전장하고 여기로 옵시다. Fetch and store controller determines whether we put the contents of the memory into a cell, MDR, or put the contents of the MDR into memory cells. Okay, that depends on the design. This is important. Cache memory. Cache memory. Cache. What do we know about the cache? 일반적으로 cache 하면 들어본 사람. Cache. What is it? 캐시가 뭐야? 현금 말고 cache. 스펠링 틀리지? Cache memory. 뭐야? cache memory 하면 뭐예요? 오, 맞아요. 비슷한 개념. 어디서 들었어요? 내가 얘기했어요? 아니죠? 워드 공부할 때? 맞습니다. Cache is the concept of cache being used everywhere in the applications they use, internet they use, but it's something like what she said exactly the same. The things that you might be using soon, let's put it nearby me. So if I'm thinking that I'm gonna need this portion of the data, let's keep it in the memory space so I can read it faster. That's the basic idea for cache. That's because this property can hold. Principle of locality. Principle of locality. When the computer uses something, that it will probably use it again. Very soon, it will probably use the neighbors of this item very soon. What does that mean? So if there are some figures that actually take a snapshot of the memory. 어떤 나중에 찾아보면 그런 거 있어요. Snapshot of the memory. And if maybe my program was asking data from this portion, let's say, later there is more chance that high chance that they will ask data from next two positions rather than somewhere below. That's the property of principle of locality. So they put nearby data close by so that you can get it faster later. 이런 성질을 가지고 있기 때문에 가까이 있는 놈들 메모리에다가 이렇게 같이 갖다 놓으면 지금은 얘를 읽는데 얘를 읽을 가능성이나 얘를 읽을 가능성이 생뚱맞게 떨어져 있는 애 읽을 애보다는 훨씬 높으니까 얘네도 먼저 여기다 갖다 놓는 거예요. 자, 갖다 놓는 거. That's the idea of cache. CPU that we looked at from Henry website. Cache memory, large, expensive, small, less expensive. Why? Cache memory, expensive. Again, going back to CPU, cache memory, large, expensive, small, less expensive. Why? Yeah. If you have a large cache memory, maybe I can put data more. But I'm not so sure it will be used soon or not. So I'm taking my chance. So if I have a large cache memory, maybe I write more and take a chance. If I have a smaller memory, then my chances of those memory space being used will be less. That's fine. And if it's a nearby CPU can take it right away. It's faster process, for example. So, makes sense, right? Cache 또. Or cache in the internet. Where do you use the cache in the internet? 좀 다른 개념 아니다. 하지 말자. 그건 더 헷갈릴 수도 있겠다. Principle of locality. It's very, very important concept. But what might be the potential problem of this approach? I'm getting the data that most likely to be used in the future. So I store. What might be the potential problem of this approach? 문제가 있으면 뭐가 있을 수가 있을까? if these are not being used later, right? If so, then maybe I should take it out from the cache memory. Is this a good idea? Which one to take it out first? Which one to write to a cache memory? Who makes those decisions, right? You don't know whether those things be used now or later, but you wanted to have maximize the performance of the cache memory. So there should be a reasonable algorithm to select a memories, data to write to the cache memory or remove it from cache memory. 앞에 뭐 principle of locality는 그렇다 치지만 저게 안 맞을 수도 있잖아요. 그러면 썼다가 지워낸단 말이야. 근데 재수 없이 지워내자마자 또 쓰다가 또 불러 갑자기. 그럼 어떻게 해? 그러면 뭐 손해를 좀 보겠죠. 되기야 되겠지만 다시 불러다 캐시에 쓰고 하겠지만 조금 느려지겠죠. Who decides that part? Who fetch, who remove, who store? 그렇죠? 알고리즘이 있겠죠. What might be the dumbest algorithm to do that? Dumbest algorithm to manage a cache memory. dumbest pseudocode. 뭐가 있을까? Random. Just remove anything. And put something that you like using random functions. That might be working. It's better to have a cache memory than not having one. So just write down one random algorithm. That's good too. 잘 될지 안 될지 모르겠죠. 그렇죠? 그래도 없는 것보다는 나을 수도 있으니까. This is actually how the system will look at your memories. Going to this. 이건 조금 그렇긴 한데. This is a memory space, two-dimensional memory. From the first half, so using n bit, this is representing the memory location of the data that I need to read. So n divided by 2, first half of the bit, we're representing the row. Second half bit representing the column. So we do, given the number, we do a decode. 여기서 왜 decode를 해야 될까? Giving a simple number, I like to get the exact location of which is the larger size of the bit. So first bit is pointing here. Second part of the bit may be pointing here. This is a location that I need to read. For example, like this. So the address information that is written in MIR, memory address register, this is special memory, not this memory, other type of very smaller memory space, have this n-bit information. Using that n-bit, I can find out where my data is. Two-dimensional, first half is row, second half is column. And then read it, fetch, store, and put that in the MDR. The data that I read from here, MDR, then maybe my program somewhere in my program will read data from this MDR and use that value to compute something. Maybe I wrote a 2 in this location. 2 will be stored in MDR. So this is a cycle of accessing memory space, writing to a memory, getting the data from the memory. Okay, two-dimensional representations. 나중에 나오면 메모리 스페이스 막 저걸 3개로 나눠가지고 하면 테이블에 막 더 걸쳐 들어가기도 해요. So that's a basic idea for building a memory and cache. Important principle of locality, property that we need to focus on to do that. 근데 나중에 안 나오고 나중에 나오지만 가격으로 보면 CPU 옆에 붙어 있는 캐시 메모리가 제일 비싸고 램이 그 다음이고 제일 싼 게 뭐예요? 그 다음으로 싼 게 뭘까? 하드디스크는 뭐 몇 테라에 10만 원도 안 하죠, 그렇죠? 그리고 내려가면 또 제일 싼 거 뭐 테이프도 있을 수 있고 DVD도 싸잖아. 그죠? 그런 식으로. 근데 싸주면 어떻게 돼요? 느려. 그죠? 거꾸로 올라오면 빠르고. 다 돈하고 관련될 수 있어요. Input and output of the mass storage. Mass storage. Like I say, hard disk is a mass storage unit too. Magnetic tape, backup tape. Anybody seen it? It's a big tape board. 그 옛날에 테이프 같이 이따만한 거. 팔에 이렇게 끼고 다니는 애들 있어요. To back up those records, like in banking systems. Input and output I/O unit, device that allows the computer system to communicate, interact with the outside world, as well as store information. Simply put, your keyboard and mouse and screen. You have to give an input to the system, right? You're doing an interaction between the two. But it seems they all going through a one path. 그죠? Memory, ALU, or CPU, I/O, keyboard, but they all seems to be using the same path. So if these two are communicating, should I wait? Should I wait? When these two are communicating, I like to send something to CPU too. Should I wait? Or can I do that? CPU가 뭐 하고 있으면 내가 키보드 누르면 안 보여요? 그렇진 않죠. 그렇다고 이렇게 동시에 보내게 해놨을까? 아니겠죠. So there are issues to which one communicate to which one first. There should be an order of doing this. 지금 우리가 키보드 치면 보이고 CPU가 딴 거 이거는 우리가 나름대로 안에서 스케줄링을 해서 실제로 동시에 하는 것처럼 보이지만 실제로는 저렇게는 안 돼요. 기다려야 돼. 하나가 끝날 때까지. Volatile memory information disappears when power is turned off. When you shut down your computer, push the power button, shut down your computer. What happens to your data? 하기야 뭐 요즘엔 너무 좋아서. What happened to your data? Some of them are gone because those data are stored in the RAM memory. If this RAM memory doesn't have a power, all 0101 disappear. Of course, your system nowadays, they do a constant backup to the hard disk, so you don't experience that much. You don't seems to be experienced that, but actually the things will be in this memory will be gone. But many of you mentioned of USBs or 뭐 있냐? SD card. Those things without the power information is being stored, right? Volatile memory, non-volatile memory. Things that disappear, that does not disappear when the electricity is not there. Role of mass storage devices such as disk and tapes and memory chips. 플래시 디스크나 뭐 이런 거, SD 카드나 그런 거는 전기 없어도 되죠? 그죠? Okay, I think I'll stop here today.